we'll have the three talks from the student teams that participate in the pod competition. So we're going to start with EPFL, and I'm pleased to introduce Denis Tudor, who's the team captain. I have to mention that his team was one of the three finalists yesterday, so it's super exciting. Congratulations.
So thank you for the invitation. I'm Denis Tudor, I'm team lead of EPFLoop. As Radu said, we qualified in the first three teams, having the highest ranking of the competition in terms of the safety of the pod. But we obtained just the third place, even if we had better expectations. That imply three pressure vessels. As you can see in the image, we have a main pressure vessel where we have all the electronic parts of the pod, plus two lateral pressure vessels where the battery system are placed. Here we have a more detailed image with the pod design. So we have used the synchronous machine in order to obtain the propulsion, the traction of the pod inside the vacuum tube. We have a Brusa motor and a Brusa inverter, a Swiss-made product, plus two braking mechanisms that are similar, and vertical and lateral stability provided by the wheels clamping the rail. Here is the pod. I will go into details for every subsystem a bit later. Here is the pod that we have built, and it's similar with the design that we had, plus two contrast sensors situated in front of the pod to know exactly where the pod is situated in the vacuum tube. So, in order to validate the power electronics that we have had in the pod, we built a flying inertia wheel of 220 kilograms that perfectly imitate the inertia mass of the pod. And also we tested the battery system, the discharge rate of the cells. Also we have built, this is a PDF file, so I had the video here. We have built in EPFL campus 60 meters of rail, where we validated our AI algorithm in order to estimate correctly the position of the pod in the tube. So yesterday, 2 days ago on Saturday, we had an open air Hyperloop test where we achieved in 300 meters 220 kilometers per hour with half of the power and half of the preload applied on the rail through the wheel. I will show you exactly the mechanism a bit later. So we expected to have about 480 kilometers per hour at this competition. But after Saturday, our expectations were lower, and we saw that we can go above 500 kilometers per hour with a torque of 385 Newton meters, and with a preload that it's pressing correctly the wheel to the rail. So the chassis and the stability mechanism are formed by springs and shock absorbers that clamp the rail through wheels, and we have here the pressure vessels that are made in carbon fiber, and they were tested in vacuum chambers inside our campus. Here we can see the connectors that we used. They are similar with the Formula E that are made by Lemo. And everything in the main pressure vessel was based on the electronics, and the main component that we had in the main pressure vessel was the inverter, because it cannot resist to the low pressure atmosphere. As you maybe know, there are teams that they didn't put the inverters in pressurized vessels, and they actually burned everything and they short-circuited the batteries. As I told you, the traction of the pod was through a wheel that was on a gear ratio optimization of the radius of the wheel to have a maximum speed at 970 meters. with the best acceleration of 500 meters. Here we have more details about the propulsion system. This is the wheel that I was talking about and the motor. And here is the flying inertia wheel that has 220 kilograms and the preload mechanism that is an actuator that press the wheel into the rail or into the load that we have under the motor. So the corner speed of the motor is about 4,000 RPM. And what happened yesterday with the max speed, we achieved just 85 kilometers per hour because we forced the motor table to be at 110%, and we actually applied 25% more preload on the wheel, and all the energy stored in the batteries was actually melting the coating of the wheel, and we have after 5 meters in our data we achieved 55 kilometers per hour, and the coating was burned, and after that it was just aluminum into aluminum that provided the slipping of the wheel, and we were not be able to accelerate more. But in the nominal way and with a better coating, we're expecting to have 520 kilometers per hour after 1,000 meters, plus the braking mechanism that are be able to provide 3G of deceleration. They clamp the rail super tough. There is a pneumatic mechanism, and we're expecting to brake around 1,275 meters. So, as I told you, for the propulsion, you use the synchronous machine by Brusa. They are used actually in Jaguar, in all the electrical Jaguar cars. This model of the motor is the most powerful one, with a maximum speed of 13,000 RPM and a rated power of 185 kilowatts. For this, so this is how we started to design the pod. We just choose the propulsion mechanism, and around this we started with batteries and the chassis that was made in aluminum. So this is a pack. It's a pack designed by the team and 3D printed. And those are the connectors between every cell. We had around 350 cells in our pod provided by Kokam. We'll see later the specs. So we had in every pack we have 12 packs, and every pack contains 3P10S. So this is the Kokam cells. There are 3 in parallel and 10 in series with a BMS with a CMU situated here. And between the cells, as you can see, we have a black zone that it's a foam in order to split the hot spots inside the batteries. So after that, after having this pack here, we just mount 2 packs with the wiring made actually integrated in the mechanical box with 2 CMUs in order to measure for each 3P the voltage and the temperature. And in each pressure vessel that I showed you, in the lateral pressure vessels, we have 6 packs, actually 3 integer packs. So the battery system and the battery system was made in house by us, and we have a maximum discharge current for a single cell at 30C around 150 amps, and the configuration that we choose, it's 460 volts that is maximum allowable by the VSI. So every pack that we have on the pod, it's around 42 volts. We choose this option due to the security reasons, because under 50 volts is still safe to handle the battery packs, even without gloves. Actually, yesterday we discharged the batteries around 620 amps, but we can go with a peak discharge current of 750 amps. So we have a maximum request power during the run due to the decreasing of the voltage, dropping voltage. We have just 180 kilowatts with a total capacity of 15 amp hours. Here, so the most interesting part of the pod actually were the batteries, but also the flight system architecture, because we had, SpaceX asked for several type of sensors for every pressurized system to have a pressure sensor, obvious things. But for that we have done two options to approach to move the pod into the rail. So we had an autopilot that is be able to estimate the position of the pod into the tube with 300% safety, and we had also manual mode in order to control every actuator that we had on the pod. So the autopilot was based in a linear state estimator that implies two contrast sensors and the encoder from the motor. And the encoder of the motor is actually based on 3 different measurements that are in the hardware, and those are some results from our rail inside the EPFL campus. So we just tweak the measurements given by the contrast sensors on the left and on the right of the pod in order to see exactly how the algorithm behaves. So also, we had the speed integration of the motor with green. So having a big error and having a maximum, very big probability to miss a stripe inside the vacuum tube, we had tuned our algorithm with big errors, because this algorithm is based on the maximum likelihood of the system. So this is our pod for this year. Unfortunately, yesterday we were not able to accelerate at 520 kilometers per hour due to the coating of the wheel and due to the traction control. But the pod was ranked with the highest points. Who participated at SpaceX Hyperloop Pod Competition? There are some green boxes that you have to accomplish in order to get in the final 3 runners. So we got the maximum ranking of the points due to the reliability of the system that we have implemented. Yeah, so next probably it will be something implemented in Switzerland, and we don't guarantee we'll participate next year for the competition.
All right.
Thank you.
So much.
Thank you.
We'll take one quick question.
Yes.
Navigation system. So you use encoder wheels, contrast sensors?
Yes.
Do you use any